Hello. I hope you guys can hear me. Let me just change to full screen. Yeah, wait, hold on. Okay, never mind. Anyway, so I did sequences and series last time. I'm going to be continuing studying calculus too. I studied the first two subchapters. Sequences. Let me open this. Quickly try to go over what I remember. Also, it's been quite a while since I did my last stream. So, a sequence is a pattern of numbers like 1, 3, 5, 7, and so on. Here, the pattern is that the numbers are adding plus 2, or I can have a different pattern 2, 4, 8, 16. Here, each term is an exponent of 2. So, a sequence. So, this sequence would be represented like this. This sequence goes till infinity, or actually, this sequence goes till 4. And then this sequence over here, it goes to infinity. So this one would be n plus 1. N is equal to 0 to infinity. There's a special sequence called arithmetic. So this is a special sequence called arithmetic sequence, where you take the first number, let's call it a, then add it by some constant, let's call it t. This is the first number, this is the second number, and then this is the third number. Oops. And then this is the fourth number. So a particular term would have, let's say n is 1, 4, so particular sequence would have nth term would, actually let's write it in text. Nth term is a plus n minus 1 d. This is the arithmetic sequence. Also, our so if the numbers are listed out like this, then it's a sequence, but if you're adding the numbers, then it's a series. So an arithmetic series, arithmetic series would be like this. S is equal to a plus d, then plus it with a plus 2d. Well, if the uh, sequence is infinite, then the series would be infinite and the total sum would be infinity. But let's say it's a finite sequence, so the series is finite. So we have, and then there are n numbers of terms, arithmetic series with n terms. Okay, let's do n, and let's do k terms. Then n is one specific term, then k is the total number. K minus 1 d. So if we add up the first and the last one, so 2s, right? If we reverse it, a plus k minus 1 d plus it with a plus k minus 2 d plus it with a plus d plus a. And now we add the first and the last one. So 2s would be, this is 2a plus k minus 1d, k minus 1d, and then this over here, still 2a again, but d plus k minus 1, d plus k minus 2d would be k minus 1d. Similarly over here it's 2a plus k minus 1d. A plus d plus it with a plus k minus 2d is 2a plus k minus 1d. So basically every time you add the first and the last one, it will always be 2a plus k minus 1d. This makes sense because when you're adding plus 1, when you're adding plus d, you're going minus d when you're going in reverse. So the sum of all of them would be same. So this means if I divide both sides by 2, it's half. And this is appearing k times, which is write it like this. K over 2 2a plus k minus 1 d. Why is this not loading? I think when I have two tabs open, then it doesn't load properly. Like two tabs with the with both open stacks. I don't know what's happening. Anyways, this is the sum of the arithmetic series k over 2 times 2a plus k minus 1d. And we have another sequence called geometric series. Let's start with the sequence first. So it's like, this is an example, 1 times, I think the second one was an example of geometric series where it's multiplying by a common number, by a constant ratio. So for example, I have 5, then times 2, and then times 2 again, then times 2 again, and so on. A sequence defined as the first term times r n minus 1 is a geometric sequence. So it's like a, then a times r, over here r is 2, then a times r squared, a times r cubed, and so on. So the third term would be a to the power a times r to the power of 2. Now what is happening? The fourth term would be a times r to the power of 3. So the nth term would be a times r to the power of n minus 1. I think as soon as I press the refresh button, it then loads. Anyways, a sequence. Now let's try the series. Series would be like a plus a to the power of r plus to the power of r square all the way till a to the power of k. Should I do k or k minus 1? Okay, let's do k minus 1. There are k terms in total. So the last one would be a to the power of a times r to the power of k minus 1. So then if I multiply this with r, I have ar times it by ar squared times it by ar cubed plus it with ar to the power of k. So if I do s minus rs, this ar will cancel out. These two ar square will cancel out. Ar cubed will cancel out. Ark minus 1 will cancel out, and we will be left with a minus ar to the power of k. And we can extract s out. You can extract a out. And then this would be s a 1 minus r to the power of k, or 1 minus r. This is when the series terminates. Now let's think of another example where the first term is 1 and the ratio is 1 over 10. So times it by 1 over 10. Then the next term would be 0.1, and then the next term would be 0.01, then the next term would be 0.0 till infinity. So then the series, if we add them all up, it would be 1.111 so on. So 1 point infinite ones. So this sum, it reaches a limit, which is 1.111 so on. So if we have s 1 minus, this is the sum to infinity, if this r is more than 1, then every term over here would be greater than the term over here. So for example, if it's 2, then the sum would be 1, 2, 4, 8, and so on, and the series would go to infinity. However, if it's if wait series is if r is between 1 -1, then the next term would be smaller than the previous term. So every term in the sequence would be approaching a limit, and the series would be approaching a limit as well. Then limit k to infinity of s would be the in this equation, k only appears here to the power of s. If we take it to the power of infinity and r is between -1 and 1, then r would approach 0. And 1 minus 0 is 1, so a times 1 is a. So when it goes to infinity, the sum is a minus 1 over r. Okay, that's the main part. So they talk about bounded. Basically, if the sequence is approaching a particular value, this sequence, for example, it will never go below 0. 0 is the lower bound, and it won't go above 1. So each term in the 0 would be between each term in the sequence would be between 0 and 1, and then the series would approach a limit. We did infinite series as okay. We were just doing infinite series right now. Let's go to the next chapter. In the previous section, we determined the convergence or divergence of several series by explicitly calculating the limit of the sequence of partial sums. A series an over here is a particular term. So basically, for this series, a0 is 1, a1 is 0.1, a2 is 0.01, and so on. So a series, the sum of this is the sum of its terms, being convergent is equivalent to the convergence of the sequence of partial sums as k approaches infinity. To verify this, notice that from algebraic properties, limit as k approaches infinity is equal to limit as k approaches infinity, the sum till k minus the sum till k minus 1, and then s minus s is 0. Therefore, if the sum converges, the nth term the n term a n approaches 0 as n approaches infinity. An important consequence of this fact is the following statement. If a n does not approach 0 as n approaches infinity, then the sum diverges. This is known as the divergence test because it provides a way of proving that the series diverges. If limit of an where n goes to infinity is equal to c, which is not 0, or limit does not exist, then the series diverges. Oh yeah, because if you're summing the constant c. Yeah, that makes sense. If we take this example over here, for example, there's a sequence like this. So the first one is 2, the next one is 2.1, next point is 2.11, next point is 2.111. This is not exactly a geometric sequence because that's not the ratio is not constant. If we take the limit to infinity and to infinity, n is a particular term. Sorry, an is a particular term. This is a0, this is a1, this is a2. So if we take it to infinity, then this would be the quote unquote last term. This is what it's approaching, 2.11111. And if we take the sum of this, it will definitely be infinity. Because it's just like adding infinite 2's. If infinite 2's adds up to infinity, then this series will also go to infinity. So the only time series converges only when the sum, limit n is equal to 0. I'll write this in text. Series converges only when this condition is true. Divergence test. For each of the following series, apply the divergence test. If the divergence test proves that the series diverges, state so. Otherwise, indicate that this divergence test is inconclusive. So sum to infinity n to n over, hold on. So limit, and this is n 3n minus 1. Yes, my n looks like an h. Divide both sides by n. So 1 over 3 minus 1 over n. As this approaches infinity, we get 0. So since the limit does not approach 0, I mean, the total limit does not approach 0, it approaches 1 over 3, then the series would be divergent. Uh, 1 over n cubed, this series is convergent because 1 over n cubed approaches 0 as n goes to infinity. E to the power of 1 over squared. This series, okay, 1 over n squared approaches 0, and e to the power of 1 over n squared would approach 1. Wait, isn't that a L'Hopital case? Limit as n approaches. No, no, no. I think in the L'Hopital case, the both this and this need to change. Because this remains e in all the series. 0, 1. So diverge, converge, diverge. Wait. What do they mean by inconclusive? Oh, I see. The harmonic series 1 over n diverges. Okay, wait. Series converges only when. Wait, let me change this. If this is the case, then this implies series converges or inconclusive or diverges. If the series converges, then the limit of a to the an goes to 0. But if the limit of an goes to 0, if we know this information, then the series either diverges or converges. Integral test. In the previous section, we proved that the harmonic series diverges by looking at the sequence of partial sums. Okay. For those of you who don't know, a harmonic series is like 1 plus half plus 1 over 3 plus 1 over 4, so on. The limit n approaches infinity of 1 over n is equal to 0, but the harmonic series diverges. So this is like one of the exceptions, one of the special case. In this section, we use a different technique to prove divergence of the harmonic series. This technique is important because it is used to prove the divergence or convergence of many other series. This test, called the integral test, compares an infinite sum of improper integral. It is important to note that this test can only be applied when we are considering a series whose terms are positive. Okay, let's see what they do. So this is 1 plus half plus 1 over 3. So we are taking the integral from 1 to k plus 1. I don't understand why. So 1, 2, 3 all the way till k. Why k plus 1? Therefore, for each kth partial sum is k satisfies. Why are we taking k plus 1 and not k? Is k. Oh, this is, no wait. This says greater than. It would be greater than the area under the graph of 1 over x. Hold on. This was my website. Since limit k to infinity approaches infinity, we say that the sequence of partial sums Sk is unbounded. Therefore, Sk diverges, or consequently, this sum also diverges, and consequently, this sum diverges. Oh, I see. This area over here. Wait. We're taking the area of squares. Actually, keep the grid. When x is 1, y is 1, x is 2, y is half, x is 3, y is 1 over 3. So, so this area is 1, this area is 1 times half. So 1, this square would be 1, and then this over here would be half times 1, which is half, and then this here would be it. Can I draw on this? Hold on. Yeah. This here would be 1, and then this here would be half. Oops. Half times 1. This area would be 1 times 1. This would be half times 1. And then this would be 1 over 3 times 1. This whole area over here would be 1 over 4. And these are the upper bounds, the area under the graph. So 1 plus half plus 1 over 3 plus 1 over 4 is the upper bound, the area under the graph. This can be done with any function, right? Where the limit approaches 0. As long as the integral is like the lower bound. Well, that's why we are doing k plus 1, because we are considering this from 5 to 6. But this only works when the integral is the lower bound of the sum. Now consider the series 1 over n square. Right. One over n square. So this area is 1 times 1. This area is 1 times half. This area is 1 times 1 over 3 square, 1 over 9. This area is 1 over 16, and so on. And then the integral from 1 to 5 would be the lower bound of 1 plus half plus 1 over 9 plus 1 over 16. Like it would be lower than that. They do 1 plus, they don't do k plus 1. Like I think this sum should either be the Riemann right sum or the Riemann left sum. And assuming that the graph goes concave down, no, concave upright, assuming that the second derivative is always positive. And then the Riemann left sum would be a lower bound, would be too low, and the Riemann right sum would be too high. You can extend this idea to prove convergence or divergence for many different series. Suppose the sum is a series with positive terms an such that there exists a continuous positive decreasing function f, where f of n is equal to a n or positive integers. Then as figure 1.41, as in 1.41a, for any integer k, the kth partial sum is k satisfies a1, a2, a3, a4, a6 from 0 to k, or from 1 to k. Now wait. From 1 to k plus 1 is this b. What about a? A is from 1 to k. 1 to k. 1 to k plus 1. 1 to k. Okay, I think I understand. 1 to k plus a1. Suppose an is a series with positive terms an. Suppose that there exists a function f and a positive integer n such that the following three conditions are satisfied. F is continuous, f is decreasing, and f is equal to an for all integers n greater than or equal to n, capital N. Then the sum is, then both of them converge or both diverge. Mm. Although convergence of this implies convergence of the related series, it does not imply the value of the integral and the series are the same. They may be different and often are. Okay, using the integral test. For each of the following series, use the integral test to determine whether the series converges or diverges, assume that all conditions for the integral test are met. Okay, let's try this. 1 over square root 2n minus 1. Where does it start? From 1. 1 over root 2n minus 1. An is equal to um, f of n and then f of n is, I'll write it in text, f of is always decreasing when n 1. These are the only two conditions, right? F is continuous, right? Continuous. So you have a decreasing graph and then you have 1 and then the limit as n approaches infinity, n approaches 0, so it goes here. 1, 2, f of n should I take the upper bound? Yeah, I should just take the upper bound. 3, 4. So the sum till k is equal to 1 over root 1 n is 1 plus 1 over 2 times 2 is 4 minus 1, 3. 2 times 3 is 6 minus 1, 5. 2k minus 1. This would be greater than 1 till k plus 1. Because the area over here is an, a1 and then a2 and then a3. This is greater than the integral from 1 to 4. So we take the integral from 1 to k plus 1 of 2n minus 1 with respect to n. Actually, nope. I forgot how you integrate this. Wait, let me think. Half becomes minus half, so I'm putting it here. Oops. Derivative of 2n is 2. So this is half. Yeah, 2, bring 2 to the other side, half. From 1 to k plus 1. Minus it with 2 minus 1. So minus it with half. Wait, this will go to infinity. Two k plus 2. There's a minus 1, so minus half. This is just k. And this will go to infinity. So this sum goes to infinity. Therefore, this diverges. The p series, the harmonic series, 1 over n, sum of 1 over n, and the series sum of 1 over n square are both examples of a type of series called p series. For any real number p, the series 1 over n to the sum of 1 over n to the power of p is called a p series. We know that the p series converges if p is equal to 2 and diverges if p is equal to 1. What about other values of p? In general, it is difficult, if not impossible, to compute the exact value of most p series. However, we can use the test presented thus far to prove whether p series converges or diverges. If p is less than 0, then 1 over p to the power of 1 over n to the power of p goes to infinity. And if p is equal to 0, then 1 over n to the power of p goes to 1. Therefore, by the divergence test, this diverges if p is greater than or less than 0. Wait, let me see. If p is 1 and p n is equal to 1 to infinity, yeah, p being equal to 1 implies s is 1 over n plus 1 over n plus, then this goes to infinity. P less than 0. No, wait. P equal to 0 implies S is... No, what am I doing? So I need to put in the value of n. So 1 to the power of 1, 2 to the power of 1, 1 over 3 to the power of 1. This will go to infinity because the harmonic series diverges. S, when p is 0, then S is 1 over n to the power of 0. Anything to the power of 0 is 1. This diverges. P is less than 0, then negative p, then this will become n to the power of p. So 1 plus 2 to the power of p plus 3 to the power of p plus it with, it is going to diverge. Now what are we left with? If p is greater than 0, then 1 over x to the power of p is a positive continuous decreasing function. Therefore, for p greater than 0, we use the integral test comparing these two. We already considered the case when p is equal to 1. Here we consider the case where when p is greater than 1. For this case, we do this, and if it's greater than 1, wait, why is it 1 minus p? Okay. Okay. Then we have, right, then we have b to the power of 1 minus p minus 1, because b to the power of 1 minus p goes to 0 if p is greater than 1. Then b to the power of 1 minus p goes to infinity if p is less than 1. We conclude that this integral is 1 over p minus 1 if p is greater than 1, infinity if p is less than or equal to 1. Therefore, this sum series converges if p is greater than 1, diverges if it's less than 1. Yeah, why would they word it like this? Just need to look at the value of 1 over p minus 1. So the first case is when p is 4. This then p is greater than 1, then it converges, right? Because p is 4. And over here p is 2 over 3, which is less than 1. So it diverges. Remainder estimate. Wait. Estimating the value of a series. Suppose we know that a series converges and we want to estimate the sum of that series. Certainly we can approximate that sum using any infinite sum, where n, any finite sum, where n is any positive integer. Question we address here is for a convergent series. How good is the approximation? How good is the approximation? More specifically, if we let Rn is equal to sum to infinity minus sum to n be the remainder when the sum to an infinite series is approximated. How large is Rn? But for some type of series, we are able to use the ideas from the integral test to estimate Rn. Let Sn be the nth partial sum of the series for all positive integers capital N. We have this is the partial sum, right? Sn be the nth partial sum. Then Rn is this. Rn is what's left of the series. N plus 1 to infinity, between n plus 1 to infinity and n to infinity. This is known as the remainder estimate. F is continuous, F is decreasing. We are finding the estimate between n plus 1 to infinity and n. Wait. So we are finding this. Wait, no. Hold on. So this sum plus this sum 1/2 1/3. We have n till infinity. Wait, I don't understand. Well, this series doesn't converge, but I just want to use an example. So the sum here would be this 1 plus half plus 1/3 and so on. Uh, and then what are we doing? I don't understand. So we have Sn plus this. Let's say n is equal to 1 or n is equal to 0. So we are starting from the very beginning. And n plus 1 to infinity is less than n. So this over here, let me use another, this over here, the area under the graph is this n plus 1 to infinity, and of course it goes all the way, but then this over here, n to infinity would be this part, right? Area under the graph till here. um I don't understand. The remaining sum n plus 1, n plus 2, n plus 3. Sum of the areas of rectangles. We see that the area of those rectangles is bounded above by n to infinity, bounded below. I don't understand, how is it bounded? Shouldn't Rn be greater than this? I got rid of my drawing. Okay, let's say we already calculated this sum and this sum. We are calculating the rest. Hold on, let me do. Never mind. Let me scale up the graph. 2 maybe. Capture. We already calculated the previous sums. We want to calculate the area of this. Then the sum here. The sum of an. No, I don't like this. This is a3. So this times 1. a3 times 1 is this area. This area is a3 plus a4 plus a5 plus a6. a3 plus a4 plus a5 and then so on is r3, right? Because we already calculated the ones before, we are looking for the remainder. But what they're saying is that the area of those triangles is bounded above by n to infinity, the integral to n to infinity, and below by integral n plus 1 to infinity. So n to infinity would be this area. And then n plus 1 to infinity would be this area. But I don't get how the purple, I get how the blue one is bounded below. It's not bounded above, it's bounded below. Oh wait, I think I get it. They're saying Rn is from n plus 1 onwards. So R3, is there an eraser here? There's no eraser. This should be not. if I do R2 is equal to from 3 onwards. So this plus this plus this plus this A3, A4, A5, A6. And then what they are saying is to take integral from here, till infinity. This is bounded above by this blue area and then bounded below by this green area. So we have the partial sum till n plus 1 to infinity. So if we include the partial sum, that is before 2, and then the partial sum ends here, right, at n, at 2. Yeah, this part, this area is part of Sn, and then the red boxes are part of, we are approximating it through the integral. So Sn plus it with the rest of the green area, so the partial sum which we have calculated so far plus the green area. And wait, yeah, that would be the lower bound. So green area would be smaller than the partial sum plus the red boxes. And then the upper bound is partial sum, the blue area, which includes this. But I don't understand. Wait, if we look at the upper bound for the integral test, I think. Hold on. I think they're using the lower bound and the upper bound over here. So the sum to infinity is from 1 to infinity. So a1, a sum of the partial sum. So we are adding the lower bound, the upper bound, and the integral is in between. Hmm. I don't understand. I think I would need better proof of this. How is it between these two? The integral here does not make sense. Like, how is it that this R2, which is R3 plus R4, A3 plus A4 plus A5 plus A6 and so on, the sum of the area of the red boxes would be lesser than the blue area of the graph? How is that? It's this part that confuses me. Rn is less than n to infinity. Uh, hmm. Sn n plus 1 to infinity. Okay, so we calculated Sn and then a n plus 1, a n plus 2, a n plus 3, a n plus 4, then b here. Given a continuous positive decreasing function f and a sequence of positive terms an such that an is equal to fn for all positive integers n, a the areas a plus n, a n plus 1 plus a n plus 2 and so on is lesser than the area under the graph. Okay, that makes sense. And b the areas is more than the area under the graph. Um, n plus 1 to infinity. Why are they doing n plus 1 here? Wait, I understood this. I'm not understanding this. I think the picture is wrong. This area should be n times 1. This is a n, and then this is a n plus 1. This is a n plus 2. That would make sense. That's why the area is n plus 1 to infinity. Therefore, the integral is either an overestimate or an underestimate of the error. Oh, I was focusing on the wrong thing. Rn is represented by the integral, right? So the remainder, this is the correct one, the red boxes. So I have n plus 1. Wait, I think I understand. Let R n equals the remaining sum we haven't found. N plus 1 plus it with n plus 2 n plus 3. And then we have this graph. Oops. Let's do this. Anyways, wait. So the remaining sums we need to find. We found this. Hold on. Let's say this is n. This is n plus 1. This is n plus 2. And then this. Oops. N plus 3. Now, alright, and then I can do this, right? This, then of course this. So the orange area is starting from here, a n plus 1. Basically, it's Rn, is what I'm trying to say. Orange area is Rn, and it's lower than um, 8. I got this wrong. So Rn, which is n plus 1 times 1. This would be the lower, this Rn is less than the area of the graph going from n to infinity. It's fair to say that. And then area, the green area is also equal to Rn, n plus 1 times 1, n plus 2, f of n plus 1 times 1, f of n plus 2 times 2, f of n plus 3 times 1. All of them are times 1. But this is like an overestimate integral from the area under the graph. Hold on, I wrote f of x here. Under the graph from n plus 1 to infinity. I think this is the proper way to explain it. So that Rn is bounded by between these two. I think the way they introduced it kind of confused me. Should I do the next chapter? Wanna see how long this is? Okay, it doesn't seem that long. Comparison test. In the preceding two sections, we discussed two large classes of series, geometric series and p-series. Wait. Okay, yeah. We know exactly when these series converge and when they diverge. Here we show how to use the convergence or divergence of these series to prove convergence and or divergence of other series using a method called comparison test. For example, consider the series 1 over n square plus 1. This series looks similar to the convergent series 1 over n square. Since each term of these series are positive, since the terms in each of these series are positive, the sequence of partial sums for each series is monotone increasing. Furthermore, since 0 is less than 1 over n square plus 1, which is less than 1 over n square for all positive integers, and the kth partial sum sk of the infinite series satisfies this inequality. I'm guessing what they're gonna check, if this is the greater one is going to 0, then the lesser one will also go to 0. Since the series on the right converges and the sequence Sk is bounded above, we conclude that Sk is a monotone increasing sequence that is bounded above. Therefore, by the monotone convergence theorem, Sk converges, and thus 1 over n squared plus 1 converges. I forgot what they mean by a monotone. Similarly, consider the series 1 over n minus half. The series looks similar to the divergent series 1 over n. The sequence of partial sums for each series is monotone increasing, and this is always true. 1 over n minus half is greater than 1 over n, which is greater than 0. So if 1 over n is diverging, then 1 over n minus half is diverging. Comparison test. Okay, I get the idea. For each of the following series, use the comparison test to determine whether the series converges or diverges. Okay, let's try n cubed plus 3n plus 1. N cubed plus 3n plus 1, which will always, now if n is greater than or equal to 1, then this over here would be less than. So 1 plus 3 plus 1 is 5. So I can rewrite this as 5. I can take 1 over 5 out. So we have this, and this converges because p is greater than 1. Do we even need the comparison test for this one? I think we do. Let's try. So it's 2 to the power of n plus 1. Wait, hold on. Did I do greater? No. Hold on. I got this wrong. This will always be greater than this. So if this is converging, it doesn't mean anything. N cubed. Um, Hold on. 1 over n cubed plus 3n plus 1. Hey, what am I doing? No, wait. Yeah. This will always be less than this. This diverges. Now for this one, just 1 over 2n I think is good enough. Because this will always be greater. No, 2n 2 to the power of n plus 1 will be greater than 2 to the power of n. So 1 over 2 to the power of n plus 1 will be smaller than 1 over 2 to the power of n. And implies this. And then some. Two to the power of n. But wait, this would be lesser than n, right? Hold on. Implies that n will be lesser than 2 to the power of n, which implies n will be lesser than 2 to the power of n plus 1, which implies 1 over n be greater than. But if this diverges, this can converge or diverge. It doesn't say anything. So maybe this. 2 to the power of n plus 1 would be lesser than 2 to the power of n plus 2 to the power of n. So we add them. Okay. So now it reverses. 2 times plus 1 be lesser than this. This converges. Sorry, I mean this. Wait. This converges. Yeah. Maybe not. Lesser than 2 to the power of n. Oh, it's a geometric series, right? So it converges. Maybe. Yeah. Need to remove this. This is a geometric series, half to the power of 1, half to the power of 2, and so on. And since r is half, it converges. Then we are left with 1 over ln. 1 over ln it ln x 0. It's undefined. Okay, anyways. N would be greater than ln of n. Implies n would be greater than ln of n. Well, this would be less than ln of n. If this diverges, then this diverges. Limit comparison test. The comparison test works nicely if we find a comparable series satisfying the hypothesis of the test. However, sometimes finding an appropriate series can be difficult. Consider the series sum to infinity 1 over n square minus 1. It is natural to compare this series with the convergence series 1 over n square. However, this series does not satisfy the hypothesis needed to necessary to use the comparison test, because 1 over n square minus 1 is greater than 1 over n square for all integers n greater than 2 or equal to 2. Although we could look for a different series with which to compare sum to infinity 1 over n square minus 1, instead we show how we can use the limit comparison test to compare the two series. Let us examine the idea behind the limit comparison test. Consider the series sum to infinity of an and sum to infinity of bn with positive terms an and bn. This and is within the latex for some reason. I now evaluate this. If the limit to infinity reaches a limit for n sufficiently large, then for n sufficiently large, an is approximately equal to L times Bn. Therefore, either both series converge or both series diverge. For the series 1 over n square minus 1 and 1 over n square, we see that n square over n square minus 1, the limit is 1. Since 1 over n square converges, we conclude that 1 over n square minus 1 converges. The limit comparison test can be used in two other cases. Suppose limit of an over bn is 0. In this case, an over bn is a bounded sequence. As a result, there exists a constant m such that an is less than m times bn. Therefore, if bn converges, then an converges. Oh, I see. Wait, I don't see. If the denominator converges, right, then the numerator converges. What if the denominator diverges? Wait, the limit is 0, then for large n, a n gets closer, the numerator gets closer and closer to 0, right? Isn't that enough to say that it converges, or do we say it's inconclusive? Series converges or diverges? But why though? Oh yeah, the harmonic series. On the other hand, suppose the limit goes to infinity. In this case, an over bn is an unbounded sequence. Therefore, for every constant m, there exists an integer n such that n is greater than equal to mbn for all n greater than equal to n. Therefore, if bn diverges, then an diverges as well. Okay, this is going to be confusing. If Bn diverges, like for the third case, if Bn diverges, An cannot be convergent. Otherwise, we would reach a limit. If Bn diverges, then the total limit gets smaller and smaller. So if An converges, then we would reach a limit, right? On the second case, if Bn converges, then An cannot diverge. Otherwise, the limit would be infinity. So An has to converge. For each of the following series, use the limit comparison test to determine whether the series converges or diverges. If the test does not apply, say so. So 1 over root n plus 1. One over root n plus 1. First, we can try to calculate this. 1 over root n. This. 1 over root n. This is converge. I have no clue. No, because p is half. But p for the p test, p is an integer, right? Hold on. Wait, hold on. 1 over root n would be... Wait. Hold on. 1 over root n would be greater. If 1 over x diverges, then 1 over root n would also diverge, right? If okay, I don't like typing in this. If 1 over n diverges, then 1 over so it diverges. Limit n to infinity 1 over root n 1 over I'm assuming this is 1, right? Divided by root n divided by root n divided by root n. Then root n goes to 1 over root n goes to 0. So that means if this diverges, if an diverges, then bn also diverges, right? Like either they both diverge or they both converge. Then both converge or both diverge. Hmm. For this case, if it's possible an can converge and bn can diverge, like it can't be the case for wait, let me, if limit n to infinity an over bn is equal to 0, then converge, diverge, no, if this goes to 0, if n converges and need to know if an converges, and let me just write it in text, an converges, then bn also converges, bn inconclusive, bn could converge or it could diverge. An diverges, then an diverges, it all depends on bn, right? Bn inconclusive, because it's possible that if an diverges, if bn an diverges, then bn can either diverge or converge. No, wait. If an diverges, bn cannot converge. If an diverges, bn cannot converge, otherwise the limit would be infinity. If an converges, bn is inconclusive. An converges, if bn converges, bn converges, then an also has to converge. An cannot diverge, otherwise the limit would be infinity. It cannot diverge, otherwise the limit would be infinity. If bn diverges, then an inconclusive, right? Bn diverges. An could also converge, and both of them, like, their division is going to infinity. I mean, going to 0. I'm unsure about the inconclusive one, but this I can understand. And the contrapositive would be if an diverges, then bn diverges. 2n plus 1 over 3n. Yeah, let's try this. Some infinity n is equal to 1, 2n plus 1 over 3n. This is an. And then let's say bn is 2n minus 1. I'm guessing, I'm not really sure about this. We get 1 over 3n. The limit as this approaches infinity it's bigger and bigger, which is 0. So then if bn converges, then an converges, right? It cannot diverge if bn converges. But we already did this, right? No, that was different. Hold on. bn converges. bn is what? bn wouldn't converge, bn would diverge. If the test does not apply, then say so. Let's try bn 1 over 3n. This would be but then bn doesn't diverge. I think the test doesn't apply maybe, or maybe there's something I'm missing. Okay, this 2 over 3 to the power of n is a geometric series. 2 over 3 is less than 1, so it converges. Okay, I should have used this then. Therefore, the total sum converges ln n over n square. Since ln, compare this with, okay, what are they doing? They applied the L'Hopital's rule. Oh, they failed with 1 over n. Now they're doing it with n square. One over n squared does not provide any information. Choosing the series n to the power of 3 over 2, we see that we are left with this. We apply L'Hopital's rule. We are left with this, which is 0. This 1 over n to the power of 3 over 2 converges. We conclude that the total series converges. Okay. Is this the last chapter? Nope. Guess I will leave this for next stream. Okay, see you guys next time. So I think I should change my background maybe.